Thank you very much for the kind introduction, and good afternoon, you all. So today's presentation, as you might understand, is about additive manufacturing, but in particular about metallic additive manufacturing. As already pointed out before and also in the previous days, it's an increasing interesting technique for several fields, ranging from the aeronautics to the automotive or the biomedical one. In most of the cases, architected cellular materials are employed due to the fact that we can tune the mechanical properties and build up really complex shapes in fast and cost-effective manner, thing that usually it's kind of difficult with common subtractive techniques. Anyhow, despite these nice features, there are still limitations on these techniques, and particularly are related to the mismatch in between the as-designed and the as-built geometry. This geometrical imperfection affects the defect sensitivity of the specimen. Indeed, these kind of specimens are have a really high defect types, which can range in between the different architecture, in the different process chosen, as well as the different microstructural defects or geometrical defects associated to the process itself. Indeed, the full widespread of these technologies is still hindered due to major concerns on structural integrity and the fatigue properties of these components. On top of this, standards for proper mechanical testing are yet to be fully achieved. And within this context, during my PhD, I studied a lot strut-based lattices, and in particular, the role of subunital elements. So the smallest unit, which is repeating inside the lattice, which is a strut. And trying to understand their fatigue behavior according to different building orientation as different kind of geometrical imperfections at 90, 45, 15, 0 degrees, but also many more. Usually, what we have noticed for at least titanium samples is that for tension-dominated fatigue regimes and fully reversible fatigue regimes, cracks start from the outer surface of as-built structures. But in particular, they start from notches that are created in between particles which are not properly molten. With this idea, usually to detect this kind of features, CT scans can be considered the golden standard for quality detection and monitoring and inspection of these specimens. Nevertheless, they are kind of costly equipments with time-intensive techniques, as well as high expertise which are required for proper characterization. The idea here is it possible to find a way to develop another method for at least a preliminary evaluation of this type of cracks and in general of an assessment of the quality of the specimen without going through CT scans? The idea of this work and what I would like to present you today is the development of a sort of efficient and cost-effective framework for the design of defect-embedded CAD models. This is not something entirely new. Indeed, also other research groups tried to do things like this, particularly in the frame of speeding up the finite element simulations of really complex lattices by, for instance, using splines, beam elements, or booleans to simulate different kind of struts and lattices. Nonetheless, what I've noticed in between all these kind of works, which are really great, is that in most of the cases, they use CT scans for retrieve the informations for splines, booleans, and beam elements of the lattices. In this work, instead, we start from really cheap and cost-effective input images, which are stereooptical or optical images. And from this, basically, the framework is built in this slide and can be divided into two branches. The first branch that aims at creating two different kinds of strut models, which are the primary profile strut model and the waviness profile strut model, through profile extraction, waviness, and roughness decoupling, as well as 3D spline generation. So it's a spline-based model. As well as simultaneously working on the particle detection and create, by applying these particles to one of the two models, the rough strut model. I will go in detail of each step of this framework in the next slides. Particularly, we will start with stereooptical images. The minimum requirement to build up these models is two images, which we detect as a horizontal and a vertical image. With each of these images, image processing is performed by image analysis, detecting of the boundaries, profile normalization, and detecting of the region of interest, which in our case is the gauge length of the specimen. And then the possibility to transfer this data from a 2D system to a 3D system, coupling two images together through 3D spline profiles. At this point, with an assumption of elliptical cross-section, and this assumption is made looking at the specimen that we had and seeing that there are parasitic masses and deformations during the process of printing that lead to moving from a circular cross-section up to an elliptical one. We are able to build up ellipses over the region of interest. These ellipses can create a sort of library data set for each specimen, giving information on the average cross-section and the minimum cross-sections, which might be descriptors which better define either the monotonic or either the fatigue properties, rather than the classical nominal value for as-built specimens at least. But particularly, we can then reconstruct primary profile models by surface structure reconstruction via Poisson algorithms. But till here, we are not yet achieved our goal, which is to embed particles basically on this kind of struts. Actually, this can be considered the outermost shell that we have created, because all the particles should stay inside the primary profile. For this reason, we need to do a step backward and getting again on the primary profiles and decoupling the primary profile into the roughness and the waviness profile. This decoupling, which has been done according to the normatives, allows then to calculate all the profile roughness parameters, but most importantly, to collect the 3D waviness profile splines. Analogously to before, we do the same process in order to create the waviness profile model. This is even worse with respect to before, but this can be considered a sort of backbone on which we can build up our actual model. At this point, simultaneously to this, we can perform particle detection. This particle detection has requirements of at least 4 images, but also more images can be used. More images are used, more precise it will be. And then for each image, we chunk the image, we divide the image in different chunks, and then we segment it through binarization masks and hot-through segmentation method. And we consider these particles detected within the region of interest in a distribution, and we compare the distribution with respect to the granulometry distribution of the feedstock powder, in this case, the TI-64, in order to bound it in between two limits and remove outliers or possible false positive or artifacts. We also check the circularity of the particles, and as you can see, there is a sort of exponential increase towards the perfect circles. So for this reason, we can assume that the particles are spherical. The sphericity of the particle is really important in order to have an efficient model, which will not cause too long computational calculation. At this point, we need to move the particles from 2D to the 3D system. We use at the beginning the waviness spline model, and for considering the two images in the groups of vertical and horizontal image, we basically consider the 2D coordinates of the system, where the x coordinate is in common with the coordinate of the 3D system, while the y coordinate of the 2D system of the center of the particle corresponds either to the y or either to the z-axis of the system, according to if it's a horizontal or a vertical image. Then the third coordinate can be retrieved from the classical equations, parametric equation of the ellipse, with the assumption that the particle will stay on the ellipse. So at the moment, we have basically hemispheres. Of course, since we have 4 different images, we will have overlapping areas. So we need also to filter out overlapping particles out of this model. At this point, we have a model with hemispheres in it, but as you know, like the surface of an as-built structure with partially molten particle is way more complex. We have necking phenomena, we have coalescence phenomena in between different particles. We want to try to achieve it. How to do this? The idea is to still consider the primary and the waviness ellipses and consider at the central point where the particle lays, consider the distance with respect to the primary ellipse. If this distance is lower than a specific threshold, the particle will stay where it is. If the distance is higher than a specific threshold, then we have 2 different cases. In both cases, we move the particle and we shift the particle so that it is tangent to the primary ellipse, which is our bounding box, basically, of the strut. Then, if the particle is still intersecting the waviness ellipse, we associate to this particle the following ellipse. If instead the particle still tangent to the primary ellipse is not anymore touching or intersecting the waviness ellipse, then at this point we shift this ellipse towards the particle. At this point, we have three different kind of ellipses associated to three different kind of particles. Then we have also a further detection logic, which is for outside or outlier particles, which are particles which are either outside the waviness and the primary ellipse. In this case, we shift it back to the primary ellipse. At this point, we are able to reconstruct the models. As you can see, the reconstruction is done via Poisson surface reconstruction, and the particles are embedded via Boolean operators in topology. As you can see from the pictures of close-ups here, we have a sort of similar approach with respect to what are in reality these surfaces, with some necking, with some coalitions in between different particles, or other particles that just bounce out of the surface. We tried to validate this model with different kind of struts of different data sets at 90, 45, or 0 degree. You probably can appreciate the different cross-section type as well as different particle distribution. So just to conclude, still a preliminary work, but we were able to implement particles on strut surface via CAD approaches in a fast and cost-effective manner. When I'm saying fast and cost-effective, it means that to build up one of these models will take less than 5 minutes. And a general validation for multiple strut data sets at 90, 45, and 0 degrees. Of course, there are still some limitations. We need to improve the particle detection algorithm, as well as the moving detection logic and the surface meshing algorithm. But most importantly, we need to do a real validation with respect to our ground truth, which are CT scans, with finite element simulation, either for monotonic properties, either for fatigue properties. Simultaneously to this, we are also building an AI-based algorithm for the random strut generation. If you're interested in this topic, I suggest you to follow the presentation on the 29th of August of my colleague Marcello Laurenti that will discuss about this. And thank you very much.